Unfortunately, most differential equations cannot be solved by separation of variables. So what we're going to do is start taking a look at different types of differential equations and look at how we can solve each type. The next type we're going to look at are what are called linear equations. Our question is going to be, how do we solve linear equations? And really what we're focusing on is what are called linear first-ordered differential equations. First order means we're only going to see a first derivative. It'll be of the form y prime, or dy dx, plus some function of x times y is equal to some other function of x. And how we're going to solve this is by a slick trick. We're going to multiply both sides by e to the integral of p of x dx power. And look what happens when we do that. When we do the y prime times the e, we get e to the integral of p of x dx times y prime, plus we have the p of x times e to the integral of p of x times y is equal to q of x times e to the integral of p of x dx. What's interesting here is, if you note, if I were to take e to the integral of p of x dx times y, and I were to take its derivative using the product rule, we would take the derivative of the first part, which is e to the integral of p of x dx, and then the chain rule says we multiply by the derivative of the exponent, and the derivative of an integral is just the inside stuff, p of x, times y, the second part, plus, finishing the product rule, we take the first factor, e to the integral of p of x dx, times the derivative of the second factor, y prime. And if you notice, what we end up with from that product rule is exactly what we currently have on the left side of the equation. The terms are in the opposite order, but it's the exact same expression, which means that left side can be written as just e to the integral of p of x dx times y, and then the derivative with respect to x is equal to q of x e to the integral of p of x dx. Which means if the left side is a derivative, I can underderivative it, or take the antiderivative with respect to x on both sides, and that'll just give me the inside stuff. That's the fundamental theorem of calculus. E to the p of x dx times y is equal to the integral of q of x e to the integral of p of x dx dx. Which means we've almost got the y solved for. All I have to do is divide both sides by e to the integral, and I find out that y is equal to 1 over e to the integral of p of x dx times the integral of q of x e to the integral of p of x dx dx. And that formula becomes the solution to my linear differential equation of first order. Now that formula is probably not worth memorizing, but it does kind of explain why the process we're going to go through works. So let's summarize what we've done in a clear process. The first thing we're going to do in our process is we're going to get our equation in the correct form. In other words, we're going to have y prime plus the p of x times y is equal to the q of x. Because once it's in the correct form, we can then easily find the integral of p of x dx, that middle piece. Once we have that integral solved, we can multiply by e to the power of whatever we got, the integral of p of x dx, on both sides. And the nice part about that is that the left side will become e to the integral of p of x dx times y, and the derivative of that product. And that format is going to set us up to integrate and solve the resulting equation. This four-step process is probably much easier than memorizing that formula, but at least the formula kind of explains where it comes from. So let's do a couple examples where we can watch this process work out. We're going to solve the differential equation y prime plus 4y equals 2x e to the negative 4x. Our first step is to get it in the correct form, and this one actually already is in that linear form. The y prime is alone. We've got y times some function, it's just the number 4, and it's equal to some other function, 2x e to the negative 4x. The second step says we're going to take the p of x, everything in front of y, and we're going to integrate that dx, which is going to give us 4x. Which means we're going to multiply both sides by e to the 4x. So I'll multiply both sides by e to the 4x. And when I do, the left side I know is going to be equal to that e to the 4x times y's derivative. The right side, we just have to simplify, and it's really nice here, e to the negative 4x times e to the 4x is just 1, so we're just left with 2x. And now all I have to do to solve is integrate with respect to x on both sides. The integral of the derivative is the original stuff, e to the 4xy. The integral of 2x is x squared, and that's where we're going to add our constant c. And then all I need to do is solve for y by multiplying both sides by e to the negative 4x times x squared plus the constant. And we have now solved this linear differential equation. These linear differential equations can look a lot different as long as they are able to be put in the correct form. Every single one will solve by this exact same process. So let's take a look at one last example. We're going to solve x squared plus 1, y prime plus 3xy equals 6x. Our first step is we want to get it in the correct form, which means I'm going to divide everything by x squared plus 1 so that the y prime stands alone. This will give me y prime plus 3x over x squared plus 1 times y equals 6x over x squared plus 1. Second step is to integrate the p of x. We're going to integrate 3x over x squared plus 1 dx. And I'm going to actually pop that 3 out front as a constant. And using a simple u substitution, where u is x squared plus 1, du is 2x dx, which means I'm going to multiply by 2 and divide by 2. And then my integral becomes 3/2 times the integral of 1 over u du, or 3/2 times the natural log of u, and u, we already said, is x squared plus 1. So we're going to, step 3, multiply both sides by e to this power. We're going to multiply by e to the 3/2 natural log of x squared plus 1. I'm going to do a little bit of algebra here, though. A constant in front of a log can go in as an exponent. And then e to the natural log just becomes the stuff inside the natural log, x squared plus 1 to the 3/2 power. So I'm going to multiply both sides by x squared plus 1 to the 3/2 power. I know the left side is going to be that thing times y, and then the derivative of that product. On the right side, it's nice because one of the x squared plus 1's will reduce out, leaving behind just 1/2. So we have 6x times x squared plus 1 to the 1/2 power. And we're ready to solve by integrating both sides with respect to x. The left side's straightforward. The right side, though, we're going to have to do a little bit of u substitution again to get there. If I make u equal to x squared plus 1, du is going to be 2x dx. So if we pop the 6 out and multiply by 2 and divide by 2, we actually get 3 times the integral of u to the 1/2 du, which means we have u to the 3/2 times 2/3 times 3. 3's reduce out. We end up with 2 times u, which is x squared plus 1 to the 3/2 power, plus our constant. On the left side, the derivative of the antiderivative is just the original function, x squared plus 1 to the 3/2 times y. And so to solve for y, we just divide both sides by that x squared plus 1 to the 3/2, which gives us 2 plus our constant divided by x squared plus 1 to the 3/2 power. And now we've got the solution to our linear differential equation of first order. Again, the process is exactly the same on every single first-ordered linear equation. So now it's your turn to practice these, getting used to this process of identifying the correct form, integrating the p of x, multiplying both sides by e to that power, and then we can integrate and solve. Practice is what's going to make you really good at this. So now it's your turn. Good luck.